All right, guys, so today what I want to do is to talk to you about a pretty classic example of tying together what we've learned about conservation of momentum and conservation of energy. And the example that we're going to look at is called a ballistic pendulum. So the way it works is you have a bullet or, a musket ball or some sort of projectile that's fired into a much larger, massive object that's hanging from a string or a rope or something like that. So this thing is fired into this block, and this block is designed so that the projectile will become embedded in it. So you'll have a totally inelastic collision. And once that happens, the combination of those two objects will then swing upwards at some angle. And that angle is able to be measured by a locking mechanism. So when it's hit, the object will swing up to a certain angle and then lock in place, and you'll be able to measure the angle to which it rises. You can assume that you would know the mass of both of these objects, and typically we also know the length. I drew it in green here, the length of the pendulum as well. So if we're able to measure that angle and we know the mass of both objects, we should be able to use that angle to figure out what was the original velocity of the projectile to begin with. So before high-speed video became very convenient and easy to use, this was the primary way that people would measure the speed of a projectile as it leaves, like a rifle or something like that. And even today, measuring the speed of a bullet or something like that using high-speed video is still not something that's incredibly easy. It's not something you can do with your phone or something like that. So this is one way that you could do it accurately. So we have two things going on here. We have a collision, so we know that momentum will be conserved in the collision. And we also have a situation where the object starts at one elevation and ends up at a different elevation. So it's going to change its potential energy. As it does that, it's going to slow down. So we're going to apply conservation of energy to that idea as well. All right, so let's look at conservation of momentum in this scenario. So for conservation of momentum, we have P initial equal to P final. And the only thing that was moving before the collision was the projectile. So the initial momentum of the system is mv1. After the collision, the projectile gets embedded in the larger block and they move as a unit at one speed. So we could combine the two masses like so, and they're moving at one speed after the collision, which we call v prime. Okay, now if we assume that we knew the mass of both objects, the angle and the length of the pendulum, we don't know either the starting velocity of that projectile or the velocity after the collision. So there's two unknowns in this expression. So we can't solve this straight up. But what we can do is look at conservation of energy. So in conservation of energy, what we're going to see is we want to look at it for after the collision. And the reason for that is because in the collision itself, when the block embeds, or the bullet embeds into the block, a lot of heat's going to be generated. This is a totally inelastic collision. So it wouldn't be correct if we said that all the bullet's kinetic energy here turns into potential energy at the end of the swing. That's not going to be an accurate statement. And we don't know how much energy gets lost or dissipated, I should say, in the collision. So we don't want to approach it from that perspective. Instead, we want to talk about after the collision happens and the block and the bullet combination are first swinging upwards. So the kinetic energy that they have as a combination afterwards, after the heat has been dissipated, after the noise, that kinetic energy that's left over is going to turn into potential energy as it swings up. So that's how we're going to approach that. So for that, I'll use a different color here. We'll call the height 0 at the bottom here. And we'll say that the combination has all kinetic energy in the beginning. So 1/2 times the combined mass equals the combined mass, that's a plus sign there, G, and the height. Well, we have to mark off the height here, so let's do that like this. Okay, but keep in mind that that height was not measured. So we have to figure out what that height is in relation to the things we have, which are the length of the pendulum and the angle. Okay, so if you look at it carefully, you might be able to figure this out on your own. There's going to be some geometry and some trigonometry involved in figuring out what that height is. But here's a key step. Keep in mind that the length of the pendulum arm is L. Whether it's hanging vertically or it's up at this angle, that distance is L either way. Okay, so if you look at this horizontal line I drew in red here that goes from the mass across to here to the vertical, okay, that makes a right angle at this point. And we already know that the hypotenuse here is L. So that means that this leg of the triangle between this intersection point and the top is L cosine theta, because this is the adjacent side to that triangle. So let's call that L cosine of theta. Okay. Now, the entire length from here down to the bottom is L. And this piece of that is L cosine of theta. So the piece that's left over would then be L minus L cosine of theta. So that's our height. So we can rewrite this as L minus L cosine of theta. There we go. That's a theta, not an E. Okay. Now, because we know L and we know theta and we know the masses, not that that matters because they're going to cancel, we could actually solve this second expression in red for V prime. So let's cancel these. And let's solve for V prime. So multiply both sides by 2. And we get 2G. And you could pull the L out if you like and get 1 minus cosine of theta there. So this is the speed that the bullet and block combination have after the collision. What we can then do is plug that into this momentum expression, which I'll copy down below again, and then we can solve it for V1. So let's shrink this just a bit and move it up. And then, whoops, let's take a look. So we have mv1 equals m plus capital M times v prime, which is this, 2gl, that's an L, times 1 minus cosine of theta. Okay, so if we divide the entire thing by lowercase m, we'll get v1. So v1 equals m plus m times 2gl times 1 minus cosine of theta divided by lowercase m. All right, so this is a great first look at a situation where you have conservation of momentum and conservation of energy together. It's a pretty typical question. And sometimes we might be looking for the initial velocity of the projectile. Sometimes you might be looking for the angle. So you might have to change the order in which you approach the problem. But the concept was using conservation of momentum for the collision and using conservation of energies for what happens after the collision occurs.